Hello, my name is Gábor Damásdi, and I am a doctoral student at Eötvös Loránd University. This is a joint work with Dömötör Pálvölgyi, and our topic is chromatic number of geometric hypergraphs.
There are a number of natural ways to define hypergraphs in geometric settings. We will consider the following one. We are given a set of points and a family of subsets of the plane. These define a hypergraph. The vertex set of the hypergraph is the point set, and the edges are given by the subsets. We simply take the intersection of the subsets with the point set, and those will be the edges of the hypergraph. Usually, we also require the subsets to be members of a nice geometric family, such as convex sets or rectangles. In this talk, we will only consider disks, so we will look at hypergraphs that are given by a point set and the set of disks in the plane. Of course, we are interested in the properties of these hypergraphs. We want to determine the chromatic number, that is, we want to color the points in such a way that there are no monochromatic edges. So every edge should contain at least two different colors. The first thing that we can observe is that four colors are always enough. Why is that? We can simply take the Delaunay triangulation of the point set, and we can color the Delaunay triangulation with four colors. And a nice property of the Delaunay triangulation is that if a circle contains at least 2 points from the point set, then it will contain an edge of the triangulation. So every disk that contains at least 2 of the points will now have 2 points of different colors inside it. The question is, can we solve the problem with 2 or 3 colors? Sometimes we do need 4 colors. Let's look at this example. In this example, we have 4 points, and any 2 can be separated from the other 2 with a disk. So the hypergraph is just K4, which requires 4 colors to be colored. To exclude these trivial examples, we are considering the following variant of this problem. Let's assume that every disk contains at least m points. How many colors do we need then? Clearly, this is an easier question. If we have more points in the disks, it's easier to color them. But even in this case, Pach, Tardos and Tóth showed that 2 colors are not enough. For every m, there exists a set of points and a set of disks, such that the hypergraph given by these points and disks is not colorable with 2 colors. Our main result is that we show that even 3 colors are not enough. So we construct a point set such that no matter how we color it with 3 colors, there will be m points that have the same color, and we can separate that m points from the other points with a disk.
Since 4 colors are always enough, this completely settles this question. To show our result, we had to strengthen the result of Pach, Tardos and Tóth.
We showed that there is a hypergraph that is not 2 colorable, and we can realize it in a very special way. We can roughly prescribe the position of the points on a circle, and we can also choose the disks to be very close to this circle that contains the position of the points. Let me explain some of the ideas behind these constructions. Let me start with the second one. We want to realize a hypergraph that is not 2 colorable, so let's start with the hypergraph. The hypergraph is defined based on a tree, so let's take a rooted tree, and the vertex set of the hypergraph are the vertices of this tree. There will be 2 kinds of edges in this hypergraph. The first type are the sibling edges. we take the children of each vertex and put them into an edge, and the second one are the descendant edges. We start from the root and follow a descending path to a leaf, and the vertices in this path will also put into an edge for every possible descending path. It is very easy to see that this hypergraph is not two-colorable. Let's just take the color of the root, in this case it is blue, and follow it down the tree. If we can reach a leaf with the blue vertices, then we have found a monochromatic descendant edge. If we get stuck somewhere, that means that the vertices below the last vertex are all red, so we have found a red sibling edge. Let's see how we can realize this hypergraph with disks. We start by defining an ordering on the vertices of the tree. We call this the sibling first order. It has many interesting properties. For example, the sibling edges will be consecutive vertices inside this ordering. So if we put the vertices in this order, it is very easy to realize the sibling edges with disks. As we said, we have some prescribed positions on a circle. We want to put the points very close to those, so we will put the points on the circle in this order. It is still very easy to realize the sibling edges. The harder part is to realize the descendant edges. We do that with an algorithm. This algorithm slowly updates the position of each vertex until all the descendant edges will be realized. We can also take care so that in the end all the disks are very close to each other. So, using a special ordering and an algorithm that updates the position of the points, we can show this second result. We can show that we can realize a non-two-colorable hypergraph in a very special way. The main result then follows from an extension algorithm already described by Pach, Tardos and Tóth. We will start with a small hypergraph, and we can then extend it using these special constructions to a bigger hypergraph. Let's look at this in a bit more detail. We start with a very simple hypergraph. It has a single vertex and a single edge. We want to keep extending this until we reach an M-uniform hypergraph. In each step, we will pick one edge of our current hypergraph, and we want to replace this with some other edges and vertices so that the hypergraph remains non-three-colorable. So we take several copies of this edge, and in each copy we add a new vertex. If our previous hypergraph was not three-colorable, this hypergraph might become three-colorable, but we can only color it in a special way. We need to color the original vertices in this selected edge with the same color, otherwise one of the other original edges will be monochromatic. Let's say that this color is red, then none of the new vertices can be colored with red. This means that we only use two colors for the new vertices. So if we also add some new edges on the new vertices that form an M-uniform non-two-colorable hypergraph, then we will get a hypergraph that is not three-colorable. So using these extension steps, we can extend our hypergraph until we reach a hypergraph that is M-uniform and not three-colorable. In each step, we replace our edge with some bigger edges, and we also add some M-uniform hypergraph. So if we repeat this step in the end all the edges will contain m points. We can use our previous construction if we choose the tree to be an emery tree of depth m, then we will get a non-two-colorable m-uniform hypergraph. And we can add this hypergraph in each step. We can also do this extension geometrically with disks. To see this, let's say we want to extend our hypergraph through this white circle. We put a small circle next to it and we rotate this white circle around this small circle to get several copies of the edge. The rotation have to be very small so that the new copies will contain the same points as the original edge. Then we slightly increase the size of these new copies and also the original edge and add some markers in the intersection with the red circle. Using our previous construction, we can now add a non-two-colorable m-uniform hypergraph on these vertices, or at least very close to them, such that the disks are very close to this red circle. So these points and disks will not interfere with the rest of the hypergraph. This is why we needed this special construction for the non-two-colorable case, because we want the disks to be separated from the other parts of our drawing. So this extension can be done geometrically, and hence we can build a point set that is not three-colorable and the hypergraph is m-uniform. Finally, let me mention another result. We also considered the case of unit disks. In this case, the chromatic number is still unknown. It's either 3 or 4, but we could show that our construction doesn't generalize to this case. We cannot do the same type of construction with unit disks, and more specifically we showed the following theorem. If we have a family of unit disks that are close to each other, which can be captured as they all have a common point, and then we can always k-color the points such that each disk that contains at least 8k-7 of them will contain all k colors. For k equals 2, this shows that we cannot create a construction where the disks are very close to each other, each contains at least 9 points, and the hypergraph is non-two-colorable. The proof of this theorem is based on a result of Keszeg and Pálvölgyi, which is very similar and considers pseudo half-planes in the plane. Thank you for your attention.